Alright, so welcome back to the fourth part of the third week. Here we are going to switch gears a little bit and not talk about longest increasing subsequence anymore, but talk about two problems which have interesting dynamic programming based solutions. In some sense, these are both classic problems, and again, you may have seen them before, but the first problem has the interesting feature of being what we call a pseudo-polynomial time algorithm, and the second problem is actually a purely exponential time algorithm. So both of these are a little bit different in the sense that they are not your typical polynomial time algorithms, and there is a good reason for this, and we will come back and talk about NP completeness later in week 6 or so. And at that point, we will have a greater appreciation for why we were not able to come up with polynomial time solutions for these problems. But with that background in place, let me get started with our first problem first, which is subset sum. So here again, the input is an array. Let me again denote it by A. And let's just say that this array consists of positive integers. And you're given a target, which is also a positive integer, which I'm going to denote by T. And the output is yes if there is a subset of the integers in the array A whose sum is exactly T and no otherwise. Okay, so I'm going to say there is a subset of indices such that if I were to sum just the elements corresponding to these indices, I get T. So if that happens to work out, then the output is yes, otherwise it's no. All right. So it's pretty natural that this problem is called subset sum. You want to know if there is a subset that achieves a specific sum. Now, if you think about a brute force approach to this problem, then, well, that would involve just going over all possible subsets, and that would take you something like 2 to the n iterations as you try to work your way through all possible subsets. You could probably optimize this a little bit and not try all of them, but it's still going to be something that looks like it's going to take exponential time. So our target here will be to come up with a dynamic programming based solution that improves this running time to n times t, where t is the given target. And of course, this might look like we have improved from exponential to polynomial, but I'm going to hesitate a little bit to call this a polynomial running time. It looks like, it's polynomial in the two things that are given to us as input. I should probably point out that this is an array of length n. Now that's where the n is coming from. And well, we'll come back to the issue of whether this qualifies as a polynomial time algorithm or not. But to begin with, let's see how we can even hope to achieve this running time. This would be a good time to take a break and think about how you would come up with your own recurrence for this problem. Think about what are the natural subproblems to identify, and maybe the running time is also a bit of a hint. So let me build on this idea that the running time is a bit of a giveaway. So probably with a target of n times t, we are looking at some sort of a DP table which has dimensions n and t. So let me draw this out. Let me say lengthwise, this is t, there are t columns, and height-wise, this is n, it has n rows. What do you think we should try and store in the ith row and the jth column here? Remember, n is the length of the input array and t is the target sum. So natural subproblem may be to say that let's focus on, let's say, the first I elements of the array A. So let me put down our input array here on the side. So I want to just focus on the first I elements in the array A. And I want to ask myself, can I achieve a sum of j using some subset of the first I elements in A? So that's going to be my subproblem, that's going to be my dp table. So dp of I comma j is, let's just say, true if there exists a subset of 1 to I such that if I just summed over the subset, okay, I think it was a bad idea to use j as the running index, so let me change that to k. So if we sum over just the subset, we get j. That's in some sense our local target, right? So this is my subproblem. I am looking at a smaller target most of the time, and I'm dealing with a smaller array most of the time. So I want to say, let's shrink the array up and let's also lower the bar for what we are trying to achieve in terms of the sum and see if this is doable. So again, two natural questions in terms of, are these subproblems useful? Are they useful in the sense of getting us to the final answer, and are they useful in the sense that do solving the smaller subproblems help with solving the larger subproblems, because we want to build our way up to the final answer, right? So, well, are they useful for, computing the final answer? Well, for the final answer, our target is t and the array is the entire array. So the final answer simply sits in the dp entry corresponding to n and t. So it's right here. Yes. So when I focus on dp of nt, what am I looking at? I'm saying that, okay, let's look at the entire array and ask ourselves if we can form a target of t. And that's exactly the original question. So if we can actually compute these values, then we would be in business in terms of having found the answer, right? Now let's take a minute to think about the base cases as well. That was the next milestone on our checklist. And what would be meaningful base cases here? Take a moment to think about this and come back when you're ready. So, well, if you stare at this, a natural choice of base case would be when I equals 1, for instance, because then you're just focused on the first entry in the array, and there's only one target that this can actually achieve, which is essentially the value that is in that location, right? And of course, you could also achieve a target of 0 if that is something that you have in your dp table, but I think we can always start with t being at least 1, j being at least 1 and going all the way up to t. So the base case will basically say that dp of 1 comma j is 1 if and only if j equals a of 1. Okay, once again, I am indexing my arrays starting from 1. Please be careful if you're translating this into code to adjust for the indices based on how arrays are indexed in your favorite programming language. Okay. All right, so we are done with our base case. We also are convinced that these values lead us to the final answer. So the only thing that remains to work out is the actual recurrence, right? Okay, so let's take a moment and think about what's going on with the semantics. We are asking ourselves if the first I elements admit a subset which adds up to j, and since we want to leverage our knowledge of subproblems, a natural question to ask ourselves is if the ith element actually participates in this subset or not, right? So, of course, if we have an edge case like the ith element being too large for the target, then of course it's not going to contribute because our array only consists of positive integers at the moment. So you can basically immediately go to dp of I minus 1j if it's clear that the ith element cannot contribute to the sum. But in general, what we can do is branch into these two scenarios where we ask ourselves if a of I contributes to the sum or does it not contribute to the sum. Just as before, we are in a situation where a priori we don't know which of these things is true. So maybe there is a solution in terms of the fact that there is some subset of the first I elements that does add up to j, but it does not involve a of I. Or maybe the only way to achieve a sum of j is to include a of I. But at this point, we don't really know which way it is, right? So as before, we are going to try and experiment with both. What if a of I does not contribute to the sum? Well, that just means that we have to go and shop for a solution from the first I minus 1 elements, because in this situation, a of I is not going to help out. So we are just going to ping the dp table at I minus 1 with the same target j, because the ith element has done nothing to help us out here. Okay. On the other hand, what if a of I does contribute to the sum? In this case, we can reduce our target as appropriate, because we know that a of I amount is already accounted for by including the ith element in our solution. So we can reduce our target and then look for a solution from the first I minus 1 elements in the array. So these are the two values of interest, so to speak. And of course, you could, depending on your preference, write an if statement to distinguish between the scenarios when a of I is too big for the target. Then you could just jump directly to this case like we did with our first approach on LIS. Or you could simply say that as a base case, if you have a target which is negative, then you immediately return false, because that's not something that's workable. But this is the overall spirit of the recurrence, being able to look at these two values to derive our conclusion about dp of ij. We are storing Boolean values this time, so how do you think we should combine these values? Well, the idea is that if either of these scenarios works out, then we are happy. But if both of them don't work out, then we have no hope for a solution, right? So our final recurrence is going to basically look like this. dp of I of j is dp of I minus 1 comma j, or dp of I minus 1 comma j minus a of I. That's just combining these two entries with a Boolean OR. And that's just saying that if either of these scenarios works out, then we have a way of building a solution. In the first case, if this works out, then just take the solution as is. And if this works out, take the solution that adds up to j minus a of I and add a of I to it, and you'll have a solution for j, right? So that's why we're doing a Boolean OR in this setting. And of course, you have to, complete this description by also writing out your base cases. So I'm going to leave that to you as an exercise to complete the description of this recurrence with the base cases and also convincing yourself of its correctness. What I do want to talk about a little bit more is the running time. Okay, so since we have a DP table where I ranges from 1 to n and j ranges from 0 or 1 to t, well, we have a running time which definitely looks like order nt because the computation here is clearly constant time. This whole operation is just looking up 2 DP entries and taking a Boolean OR, so that's straightforward. So the overall running time is indeed order of nt. So the question is this something that we can interpret as being a polynomial time algorithm? Well, we do have n numbers as input, so anything that's polynomial in n will check out. But what about the t that is sitting here? We don't have t as an input in the sense that we don't have t being stored in memory as is. Remember that t is just a number. So t is stored in binary when it's given to us as input, right? So if you think of the size of this input, it's actually going to be log of t, log to the base 2 of t, because that's how many bits you need to represent t on your machine, right? So the running time of an algorithm is always thought of as a function of the size of the input, okay, not its magnitude when you're dealing with numbers, right? So now if you think of t in terms of the space you needed to represent t, it takes on a whole new color, right? So I can rewrite our running time as n times 2 to the log t, where the log is to the base 2. So of course you might know that this is going to cancel and give you t, but the reason I'm writing it in this format is to make explicit what the running time looks like as a function of the input size. And as a function of the input size, this running time is exponential, right? So this is not a polynomial time algorithm. So please be very careful when you have numbers in your input. These could be edge weights in a graph and things like that. It could just be a purely numerical problem, like for example, you're given a number n and you want to know if it's prime. So when you come up with an algorithm for primality that involves, for example, checking for divisors and going all the way up to the square root of the number looking for divisors, that's again an exponential time algorithm for the same reason that you are being exponential in the log of the number, right? And the log of the number is actually the size of the input. So please be mindful of this. These algorithms are called pseudo-polynomial, and in particular this running time here is a pseudo-polynomial running time. And the reason it's called pseudo-polynomial is because it's polynomial when the number is given to you as unary. So imagine that you stored t in a unary format instead of a binary format. Then of course you have all the time in the world. You can take your own sweet polynomial in t, and that would qualify as a polynomial running time simply because your input is so generously huge. Of course, nobody really stores inputs in unary because that's just terribly inefficient. It's exponentially worse than storing them in binary. So that's not a realistic model of computation, but what's usually meant when you say pseudo-polynomial is that, well, if the numbers were small, then your algorithm will work fine. That's essentially the takeaway when you see pseudo-polynomial as a keyword somewhere. So keep in mind that this DP that we have just seen is not a polynomial time algorithm. It is, however, a valid pseudo-polynomial approach. Having said that, though, if you compare this running time with the brute force approach that we had earlier, which was order 2 to the n, in most scenarios, the DP will outperform the brute force algorithm. I would encourage you to think about on what kinds of inputs would the DP fare worse than brute force. Is that possible? Can that happen? Give that a thought. And in the meantime, let's move on and talk about set cover, which is our second problem for this discussion. So what is the set cover problem? In set cover, our input is a universe U and a family F You can think of the universe as being a collection of n distinct elements. It's a discrete set. And the family is essentially a collection of subsets of the universe U. Okay, so each Si here is some subset of U. Now, we are also given a budget You could also think of this as an optimization problem without a budget, but let me just write it down with a budget anyway. And what we are looking for is a subfamily of F such that the subfamily only has at most k sets and it covers the entire universe, by which I mean that if you took the union of all the sets in the subfamily F prime, then you would actually get the entire universe. So we want to know if such a subfamily exists, and if not, then the output would be this is not feasible, so you can simply say no. So it's possible that you're seeing set cover for the first time. If that's the case, then it will probably help for us to walk through an example. But if you're familiar with the problem, then feel free to skip ahead. So let's say our universe consists of the elements A, B, C, X, Y, Z, and we have a family that looks like this. Now let's specify a budget. Let's say that K is 2. So we are looking for two sets whose union is the entire universe. So that would mean, at least for this example, that we get to pick a set and the complement set must be contained in some other set because the budget is just 2. So do we actually have a subfamily here of size 2 that covers the entire universe? Well, it turns out that you can actually pick these two sets here and their union will turn out to be the entire universe. Let's just confirm that. We have A, B, C, we have X, Y, and Z. So everything is indeed covered, and that's what you would call a yes instance. But if we reduced the budget to 1, then it's clear that there's no single set which is the entire universe. So the answer with that slightly tighter budget would actually be no. Okay, so all right, so I hope that the definition of the problem is clear. If not, feel free to take a minute here and work through it. Make sure that you're comfortable. And now what we want to do, of course, is to actually solve this problem, and we are going to use a technique called dynamic programming over subsets. Again, just as a baseline, let's think about what the brute force algorithm would look like. Remember, you're trying to find a subfamily of the given family of elements. So if you simply try to go over all possible subfamilies of size k, then your running time would look something like m choose k, which roughly works out to something like m to the k, right? The problem with this sort of a running time is that m could be really large because m represents the size of the family. That could be, in the worst case, exponential in the size of the universe. And now you are doubling down on that and going over all possible subsets of something that's already exponentially sized. So you hit almost a double exponential kind of expense when you do that. So what we want to do, or our goal here, will be to take this and improve it using a DP approach to something that's just exponential in the size of the universe alone. And once again, this is not going to be a DP that we can eventually improve to being polynomial time. And it's a problem that we will revisit when we talk about hard problems in the second half of this course. But for now, I just want to show you a nice and clean DP-based approach to solve set cover. Again, feel free to pause here and take a moment to come up with your own subproblems for this if you would like to do that. And I hope that you had a chance to think about this. Once again, the running time was a bit of a giveaway, so you could probably imagine that we are going to somehow index our DP table or our recurrence approach by subsets of the universe U. So suppose S is a subset of the universe, and what I want to know is, can we just cover S using some part of my family? So just like we did with subset sum, we are going to just line up the sets that we have, S1 to Sm, and I'm going to make available to you just the first I sets and ask you, can you use these I sets to cover S? So in this sense, in spirit, it's very similar to subset sum. I am giving you a smaller target and I'm giving you a smaller family, and I'm asking you, well, with the smaller family, can you cover this smaller target? Okay, and just like before, let's ask ourselves if this is a meaningful thing to do. Does it lead us to the right answer? Are the base cases clear? And then we will come back to the recurrence. So before we go there, let me make the DP table explicit so we know exactly what we are storing. So I want to focus, like I said, on the smaller universe S, and I want to truncate my attention to the first I sets in the given family, right? So I want to store a value corresponding to this subproblem. And remember, we had a budget K for the overall size of the solution. And when I'm building this DP table, I could keep the budget at the back of my mind. But what I'm going to do is just find the size of the smallest family, the smallest subfamily that can cover the universe that I'm currently interested in. So at the end of the day, we will hopefully have computed the size of the smallest subfamily that covers the entire universe. And since that's going to be the best that we can do, we can answer the original question by just looking at the value in the DP table and checking if it's at most K or not. If it's not within the budget, we can say no. But if it is within the budget, then we can say yes and actually even report a subfamily that does cover the universe with the size that is claimed by the DP table. That you can do by backtracking, as we have discussed before. So let's write down the semantics here. I'm going to say that we will store here the size of a smallest subfamily of S1 through Si that covers all elements in S. So S is my current universe and S1 through Si is my current family, right? So that's my subproblem. And once again, let's quickly sort out the issue of where is the answer. Well, again, in this case, the answer is quite evident. It sits at u comma n, because at this point you're covering the entire universe using the full force of the family that has been given to you. So the answer is clearly computed if you compute these subproblems. And let's also quickly think about the base cases here. So again, you could start off with I equals 1 as being a base case. So that's going to cover any subset of S1, right? So dp of S comma 1 is going to be 1 if S is a subset of S1, and we are going to say that it's plus infinity otherwise. The plus infinity value is just to say that this was not feasible. It's not feasible to cover something that is larger than S1 using only S1, right? So that's our base case, and I think you'll agree that that's fairly intuitive. Now we can actually talk about the recurrence, and in spirit this is not very different from how we worked through subset sum. So we have a universe and we have some subset here that we are trying to cover, and we have a partial list of sets with which we are trying to cover it, right? So S1 through Si. And now, of course, we are going to try and focus on the last set here and ask ourselves, does Si contribute to our solution? And as before, there's no way that we know the answer to this because we don't know what opt looks like. But because we are computing all of these subproblems, we have the luxury of trying out both possibilities. So let's put ourselves in the shoes of a situation where Si does not belong to opt. In this case, we can just appeal to dp of S comma I minus 1, because Si is not going to make any difference. We have to fend for ourselves with the first I minus 1 elements, and we still have the same target upon us. Okay, but on the other hand, if Si does belong to opt, then we can reduce our target based on the help that we have from Si. But we have to also remember to pay the price for including Si in our solution. So in this case, we have to remember to pay 1. But then when we go deeper into the DP rabbit hole, we can actually set ourselves a smaller target, which is S minus Si, because Si is going to be in our cover, so we don't have to worry about covering those elements that are already accounted for by Si. But remember that the 1 plus here is crucial, so that you're carrying forward the size of the solution in this recurrence. We've already seen an example of what happens when you forget to do your plus ones. You don't get the right answer at all. Yes? Okay, so these are the two scenarios. Let's combine them to write down our final recurrence here. So we have dp of S comma I, and we're going to get two values from these two parallel universes that we have gone into, and we are going to be greedy and pick the better of the two values. Remember, this greedy is not the kind of blinded greedy thing that is typically wrong. This is a greedy choice between two exhaustive options. So that's why it's going to be correct. So it's going to be the minimum between dp of s comma I minus 1 and 1 plus dp of s minus si comma I minus 1. So those are the two table lookups, and the min is what helps us actually combine the two possibilities and gives us the best of both worlds, literally, right? And once again, I'll leave it to you to expand this recurrence to account for the base cases and make it complete. But in terms of running time, hopefully it's clear that this index here is going to contribute 2 to the n entries because you're looking at all possible subsets of the universe, and I of course runs from 1 through m. So our overall running time is going to be 2 to the n times n. So this is an exponential dp, but it still beats brute force, which would have been potentially as bad as 2 to the m, and m could be potentially as bad as 2 to the n. So we've gone from doubly to singly exponential in the process of writing down this dp. Okay, so I hope you enjoyed that. That's all that I will have to say about subset sum and set cover. If you are so inclined, you can take these recurrences and subject them to the same analysis that we did for the second dp that we saw for longest increasing subsequence. You can prove these two inequalities, where we know that here we are trying to store the value of opt as far as that local subproblem is concerned. So I would really encourage you to actually go through that process to convince yourself about the correctness of these recurrences. And the other thing that you can do for bonus points is to think about how you can backtrack your way through the dp to actually build up a solution and not just report a number, which is the cost. And of course, for set cover, I will say that I started off by describing a budgeted version of the problem. So as I mentioned before, to answer the yes/no question, you can simply look at the optimum value reported by the dp and simply check if it fits your budget or not and say yes or no based on whether it does. Okay, so with that, we conclude our discussions here, and next time we will meet to talk about the edit distance problems. So I look forward to seeing you then. Thanks so much, and talk soon.